I'm Nishant Kumar, and I'm the team leader for the Integrated Punch Biopsy team. I'd like to take a moment to introduce my team members, Sebastian, Abi, Bofeng, Makoto, Kalen, and Thomas. We've all worked very hard on this project. I'd also like to acknowledge our clinical sponsors, Dr. Siwon Kang and Dr. Timothy Wang from the Department of Dermatology. So we've been working on punch biopsies that are used on skin, and so here's a brief clinical background. The skin comprises 3 layers. The outer layer is the epidermis. That's followed by the dermis, and then finally the hypodermis or subcutaneous tissue. So why are punch biopsies performed? Punch biopsies are performed by dermatologists and other healthcare practitioners to obtain a sample of skin for diagnostic purposes. So this may be when they suspect an abnormal skin disorder or skin lesion. These are really important. On average, 3.8 million punch biopsies are performed annually in the United States alone. And we've actually channeled all our efforts in redesigning the punch biopsy because it's the most common kind of skin biopsy that's performed. So what is a punch biopsy? This video here is a punch biopsy being performed on the forearm of a patient. The way this works is the dermatologist would prep the area with a local anesthesia and then insert the punch tool with a rotatory motion. Once that's done, forceps are used to extract the skin sample, scissors are used to cut it, and then a suture is finally used. So the current standard of care, as many of you might have used this, is the circular punch manufactured by Staphyl Labs, Accuderm, and Medex Supply. It costs about $2 per device. In early 2000, a slight innovation was done in the field of punch biopsies with VisiPunch. It incorporated a window in the blade that provided visual cues to the dermatologist, but the device most commonly used is still the circular punch. But these punch tools are only one aspect of the entire setup. As you can see in this image here, there's a vast array of instruments that are used in the current procedure, and those involve not only the punch tool, but it involves scissors, forceps, needles, a needle driver, gauze, and suture. And some of these instruments are reused, which means they have to be sterilized and sonicated, and all that adds to a preparation time of about 2 hours and increases the total procedural cost to about $50 per procedure. So that involves the sterilization phase as well. We've actually identified problems with our clinical sponsor in each phase of the process. So the punch phase, when the dermatologist inserts the punch tool, has the following problem. If you can see here, there's no way for the dermatologist to know how deep he or she is going into the skin. And that can be a big problem when punch is done in your face or somewhere where the skin is really thick. That can lead to damage to the underlying artery or nerve. And if the sample isn't deep enough, it could actually lead to inadequate skin collected, which means another punch biopsy has to be performed, adding to further inconveniences for the patient. The next phase is the excision phase, and this is a pretty crude process, at least we thought it was. Forceps are used to pluck out a skin from the arm, and then scissors are used to cut it out. Again, depending on the skill of the dermatologist, this can sometimes lead to damage to the integrity of the skin sample. And finally, the last phase that involves the use of sutures tremendously adds to the cost of the entire procedure, and with any phase that involves needles and sutures has injury problems to the healthcare worker. So our mission when we started off this project about 8 months ago was to innovate a self-contained punch biopsy tool that integrated the current procedure to make it safer, easier, and less expensive. And we've been supported by the CBIT program, the Hopkins Biomedical Engineering Department, and the School of Medicine. So these were our engineering goals and constraints that we set when we started working. And our primary goal was to regulate the depth of the punch, as well as to develop enough force to sever the sample and collect it within the blade. We also wanted to be at a price point that's comparable to existing devices. And most importantly, we wanted to make sure we didn't significantly change the current technique so that it was adaptable to dermatologists. As with any project, we've gone through several iterations of our design. This was our initial prototype that we arrived at the end of last year. The way that one worked was it incorporated a steel wire that ran up the black handle, and it encircled the blade. It worked on a constriction mechanism, and while this worked when we did our tests inside our lab, when we actually tested this in our sponsor's lab, it failed. And so we were quick to learn that we needed to incorporate a shearing motion to cut through human skin. So it was actually tougher than what we thought it was. So this innovation was 2 spools of differing diameters, and that enabled us to develop a shearing motion. So this one worked, but our sponsor told us that he would prefer a motion more like a bottle cap being screwed on as opposed to a rotation like this. And so we came up with this crazy design where we translated the motion using gears. Our sponsor called this a pizza cutter, so we decided it wasn't useful for the clinic. And this is where we finally arrived at after a few more months. This is our final design. I'm just going to show you an exploded view of the same. So this is our handle that has a spool at the end. There's a shaft in which the handle fits. There's a depth regulator mechanism and the blade at the end of the device. And this is how it all comes together. So the blade's at the end of it, and the handle just fits into the shaft. So here are the key components of our entire setup. The first key component was the spool and the handle. The spool is where the wire will eventually roll up on. I'll show you that in a few minutes. Our magic actually lies in our wires. So we use a wire mechanism to cut through the skin. And the wire we're using is a diamond wire that's about 140 microns in diameter. It's actually impregnated with diamond dust, and that adds an uneven surface to the wire that makes it strong enough to cut through human skin. We have a shaft, which is basically the handle that the dermatologist would use to grip the device. It's the same length as the current one, so that makes it easy to use. We have a blade that has a hole and a canal in which the wire enters. It sits in the canal and exits through the blade. And finally, we have our depth regulator mechanism. So how exactly are we doing all this? I mean, what's our magic? So as I show you here, here's our blade and a closed-up view of it. So there's a small canal at the bottom of the blade that houses the wire. The way this works is one end of the wire is fixed to the spool at the end of the rotatable handle, and one end is fed from the shaft. And that encircles the blade at the bottom. As the handle is rotated, the wire spools onto the handle, and it reduces the circumference within the blade, gradually shearing the skin and cutting it like a cheese cutter does. And finally, you get your skin cut. So we've eliminated the need, so that's just the mechanism of our severing right there. That's how it works, and it would just cut through the skin. So we figured out a way to get rid of scissors, because now we use diamond wires. To retrieve the sample, we have this following method. We've designed our blade in such a way that it makes an initial incision that's 4 millimeters, whereas it fits the sample into a space of about 3.8 millimeters, and that's been sufficient friction to actually pull up the sample with it. So we've eliminated the need for forceps in this way. Here's an animation of our device in use. That's just a patient's hand with a small mole on the top. The punch tool would be brought in by the dermatologist. He or she would regulate the depth. The blue disc that you see that's going down now would lock this depth regulator in place. Once that's done, you would insert the punch tool. So again, you'd see a rotation motion to insert it in. So once that's completely rotated, the hub would regulate the depth. The dermatologist would then spin the handle on the top. Once it's completely severed, you'd be able to tell, and you just see that the skin's retrieved inside of it. And one of our ideas is using a steri-strip to close it as opposed to sutures, and I'll elaborate on that in just a few slides. So here's us testing our skin, our device. This is my hand, but that's not my skin. We just wanted to simulate what it would be like. We just try to show you here. It's about 5 to 6 rotations on average, and you'll just see that as he pulls out the punch tool, the sample is retrieved within it, and the dermatologist would use a more professional way to remove the sample, but this just shows that it works. Our next testing was to see if our diamond wire was really, really strong. So we tested it on pig's foot, which is supposed to be extremely thick, and as you can see, those are holes that are made. We then wanted to actually test if our device was cutting in a straight horizontal plane and not cutting in any shear way. And we used PDMS to visualize this better. As you can see in this video, it's completely cut, and again, our professional way of removing the sample. And that's where the sample is. And that's just showing you that it's in a horizontal cut. Finally, no test is conclusive until we tested on actual human skin. This is discarded human skin samples at our sponsor's lab, and that test was just to show you that it cuts right through human dermis. So that's the toughest layer of human skin, as we've learned. So I mentioned our blue disc earlier and our rotatable hub. That's our depth regulator mechanism. The way that works is similar to a screw, and it would just be spun on by the dermatologist. There would be markings so that he or she would know how deep the device would go into the skin. So we've spoken about how we're going to cut the sample, how we're going to retrieve the sample. we have to figure out a way to remove the sample. And the way we're proposing this is one of two ways. One method involves drilling a hole right through the rotatable handle in line with the blade. And since we know almost every dermatologist office has a Q-tip, they'd be able to just poke it out. The other method would be to have a window at the back of the shaft that would also provide a visual cue that the sample is being retrieved in the blade, and then it could be poked into a tube for pathology. Now, closure. So when we spoke to our sponsor a few months ago, we asked our sponsor, why wouldn't you use something like a steri-strip or a medical strip to close a wound? And he said, honestly, we've never really thought of it because that's just the way things have been done. We've always used a suture to close a punch biopsy. Our sponsor really believes that something like a strip would be strong enough to close a punch biopsy wound. And so we envision redesigning this strip to provide a larger surface area to close the wound, and even using mastisol, which is a medical adhesive, to enhance the effects of the strip. So to show you why our closure method would be better, here's again skin substitute before closure, and closure with the strip, and closure with the suture. I want to highlight two key aspects. First of all, the time to do this process. I mentioned earlier when I set the problems for this entire procedure that it takes about a minute to do the whole process with sutures. With a medical strip, it takes about 10 seconds, and it's just much easier to do the whole thing. And more importantly, the patient is extremely important, and as you can clearly tell, the strip is aesthetically more pleasing and also just convenient for the patient. There's no need to revisit the dermatologist or the nurse to get your sutures removed. So here's our envisioned clinical use. We've called our procedure the Pro-PET procedure. And the way that works is punch, rotate, pull out, eject, and tape. Simple over here. You insert the punch tool into the skin. You use the rotation motion to sever the skin sample. Finally, close it with a steri strip and eject the sample for pathology. And so, I just want to wrap up with these last few slides where we showed you this is the current setup of the punch procedure. And here's what we're proposing. We're proposing something way more sophisticated and compact, just one packet that will do everything for you. And this just really shows you what's the right decision. Here are our estimated costs. We believe with mass manufacturing, we'd be able to achieve a price point that's comparable to the existing devices out there in the market. I'd be happy to talk more about this at the poster session afterwards. And just to wrap up, why would we want to adopt our punch procedure? Well, it's pretty simple. Our punch biopsy is easier to perform. It's safer to use. It's a better experience for the patient, which is extremely important. And as we all know, money is extremely important in our healthcare today. And we're proposing a procedure that's about 80% less expensive. Our future testing and our future direction is as follows. We want to continue testing on pig's foot and human skin samples. We definitely want to try on cadavers to see if our prototype works completely. And once things work out, we plan to apply for an IRB for clinical trials. We'd really like to acknowledge the following people without which this project would not be successful. Our sponsors, as I mentioned earlier, Dr. Kang and Dr. Wang, Dr. Allen, Dr. Acharya, and Dr. Yazdi for their help and support, and a bunch of other professors and students who've really been useful. I'd also like to say thank you to our CBIT graduate mentor, Anastasia, for her help. And thank you. We're open to any questions that you may have.